Spatial analysis is about a lot more than just geoprocessing tools. Now, certainly, the tools and methods are fundamental, but analysis really is a capability that spans all of ArcGIS. It's the support for the data that you need, the experiences that you use to drive your analysis, and the ability to extend beyond ArcGIS, tapping into the open science ecosystem. One of our core focuses is helping you, the GIS community, get your work into the hands of everyone in your organization and the rest of the world. Now, you share your analytical work as maps and apps, of course, but you also share it as scripts and notebooks and models. One of the most powerful ways that you deliver your work is by sharing data processing and analytical workflows as web tools. Web tools can be designed and authored in ArcGIS Pro using scripts or models from ArcGIS notebooks, and now from Model Builder in ArcGIS Online. And your work extends beyond traditional ArcGIS environments. ArcGIS supports an open ecosystem for analysis and science, driven by tools like Python and Spark and R. Now, we spent some time talking about our work in Python, but the R-ArcGIS Bridge is another important piece of that story. As an ArcGIS user, you can build R-driven geoprocessing tools that work directly inside of ArcGIS Pro. And with the ArcGIS Meta package, open source and available on CRAN, you can empower our users across our organizations to read and write data, geocode, invoke web tools, and more. To share with us some of our new capabilities for publishing web tools and the new ability to access web tools directly from R, I welcome Simon and Josiah. Simon, take it away.
Thank you, Lauren. We are always working on improving your experience deploying web tools. And today, I want to share two new capabilities that come directly from your feedback: the ability to enable server-side validation for custom web tools, and the ability to publish web tools directly without using the history. In this example, I've built a tool that allows a user to upload environmental contamination sites into our enterprise geodatabase. Let's start with the Python toolbox. It checks for expected schema and data quality. This tool's validation will resist an error when the extent is outside of the target Michigan state boundary. Now I have a tool ready to go. I want to share it as a web tool so others in my organization can use it. In the next release of Pro, you can publish directly from the toolbox. No need to run it first, which can be valuable if you have done appropriate functional testing but don't have the result in the history. Thank you. In the sharing pane under configuration, I will enable the new validate capability and publish. To save time, I will access one I published earlier in the catalog, portal tab, and we can check it against some test data. First, I will intentionally pick a dataset outside of the Michigan extent to ensure our custom validation works by clicking the Validate button. It is. This quick check was run on the server using the custom Python code I showed earlier. This type of validation can catch issues before the tool runs, improving tool user experience, decreasing server load, and bring equivalency with custom Python tools in Pro. I can fix any bad input immediately based on the validation feedback without getting a failure when the tool runs. Now I've got a working web tool that uploads new contamination incidents. It can be used across ArcGIS. In this case, I have shared with my colleague Josiah, who is going to demonstrate using the same web tool somewhere new, using the R-ArcGIS Bridge.
Thanks, Simon. I'm going to introduce two new capabilities that bring the ArcGIS system and R closer together. The latest release of the R-ArcGIS Bridge introduces web tool support and access to the Calcite design system. While we R users are a mathy bunch, we also love building data-driven applications using a framework called Shiny. I've built a custom web app in R to streamline incident uploading. This app uses the web tool that Simon shared to validate new inputs. I've got a file of new incidents to upload, but before I can upload anything, I need to validate the data. Rather than re-implementing the validation logic in the client, the new web tool support means we can call Simon's service. The app captured and reported the message directly. I'll now upload a CSV file that falls within the expected extent, and after passing validation, we can successfully run the tool appending the new incidents to the web layer. Support for web tools in R means we can also tap into dozens of ready-to-use ArcGIS analysis services. I'm going to select a handful of locations and press Run Trace Downstream. We're now calling the Trace Downstream hydrology service and waiting for the results to flow right back into our app. And all of this is powered by R. With the R-ArcGIS Bridge, R connects into the ArcGIS system. So the same web tools your organization relies on can now power your Shiny apps. And with the Calcite integration, those apps look and feel like a natural part of the ArcGIS ecosystem. Thanks, and back to you, Lauren.
Thanks. Thanks, Josiah. Thanks, Simon. Helping you extend the reach of your analysis means delivering spatial analysis in all of the places that you need it most. And when it comes to big data, that increasingly means support for a wide range of cloud platforms and Spark environments. GeoAnalytics Engine is all about delivering scalable, scriptable analytical functions and tools to your own Spark environments. It includes a comprehensive set of tools and functions that allow you to craft exactly the workflows that you need. And with the latest release, we've added support for imagery and raster data. Next, Ethan will show us some of that new raster support in GeoAnalytics Engine. Ethan?
Thanks, Lauren. GeoAnalytics Engine is already a great tool for vector analytics at scale. And now, it brings that same power to raster. Let's explore this new functionality with a real-world problem using zonal statistics. But first, I'm going to actually run the zonal statistics tool live. And we can time it together as proof of everything I'm about to say. While that's running, let's explore our problem. Imagine our company wants to purchase land for wind energy development. We have a wind suitability raster, but that alone doesn't tell us which parcels we should look to purchase. Zonal statistics is a tool that will help us take this raster and enrich a polygon data set with its values to create actionable insights. To start, we'll load our nationwide wind suitability raster. This is a TIFF, but could be an image service as well. Now our raster is in a Spark data frame ready to process. We can also plot this raster right here in the notebook. Here, areas more suitable for wind energy development are highlighted in lighter colors. Next, we'll load the polygon data set that we want to enrich with this raster data. In this case, we're using a nationwide parcel data set from our partner Regrid, filtered to parcels larger than 30 acres, giving us a total of 13 million parcels to process. Finally, we're back to the zonal statistics process I kicked off earlier. It's already done, finishing in 1 minute and 7 seconds, taking advantage of Spark's distributed processing to enrich 10 million parcels against nationwide raster data. In the end, the tool produced several wind suitability statistics for each parcel. These can be used for evaluation and planning. To that end, we can write our results to a feature service to use across ArcGIS for exploration and prioritization. For example, in a web app, here my business can zoom and examine a specific parcel and its wind suitability values. And I can filter to just parcels highly suitable for wind energy development. With raster support in GeoAnalytics Engine, we were able to quickly enrich millions of parcels with nationwide raster data to power downstream analysis and decision-making. Now, back to you, Lauren.
Thanks, Ethan. Now, while it's true that spatial analysis is about a lot more than tools and methods, the truth is that every year, a huge part of our work is still making sure that you've got the best tools and resources at your fingertips. That includes advances to data engineering, graph analytics with ArcGIS Knowledge, spatial machine learning, and so much more. At the heart of it, the steel thread that connects all of our work is the science of geography. Well, science can sometimes feel distant, the domain of academics and researchers. But the truth is, the GIS community is one of the best examples of where science hits the ground and makes an impact. The work that you all do really matters, driving decisions and influencing people's lives all over the world. And you take that responsibility seriously. I've been lucky enough to be part of this community for over 20 years, and I've heard many of you ask similar questions. What classification method should I use to visualize my results? What bin size should I use for aggregation? How do I know if my model is good enough? These are really hard questions. And the truth is that mostly they don't have one right answer. But asking these questions really matters. And it matters now more than ever. And we're working to build tools to help you make these decisions in ways that build confidence and that are scientifically defensible. Because the stakes are really high, and you need the best science in your hands. Next, Sharmishta and Alberto are going to show us some of the new tools that we've built to help you make these decisions confidently. Sharmishta?
Thank you, Lauren. Natural hazards cause significant impacts on communities, infrastructure, and economy. And exploring patterns can help us understand how it impacts different areas. Today, we are looking at over 100,000 flash flood events from the last 30 years. Since it is difficult to find any meaningful pattern here, our next common step is to calculate a density surface to transform these discrete events into a continuous surface to see the extent and concentration of these events. We now see an emerging pattern in the Northeast and the Midwestern states. But here is the problem. The interpretation of the surface is inherently subjective, and it depends entirely on the classification and the visualization. We need an objective and statistical way to define these concentration zones to support data-driven decision-making, and that's exactly what the new Volume Percentile Contour tool does. This tool creates a boundary of the density volume for a specified percentage. It can also create contours of multiple percentile values. Here, these boundaries represent 25th, 50th, and 75th percentile density volumes, respectively. Now that we have some understanding of the flash flood concentration, let's take a look at two other major hazards: heavy snow and tornado. These hazards often impact the same geographical region during the same time period. The ability to do this kind of comparison is another strength of these contours. Since the 50th percentile is the area that contains half of the total volume, we will focus here for the initial planning. By overlapping areas of flash flood concentration with heavy snow and tornado, we can find out which areas experience more than one major hazard. Now, over time, climate patterns have shifted and land use has changed. We can also use these contours to look at a 3-year interval to see how it changes over time and which counties get repeatedly exposed to these 3 major hazards, represented in red here. These areas become priority for planning and resource allocation. The ability to transform a subjective density surface to a quantitative information product is crucial for building understanding and informing decisions. I will now hand it over to Alberto to introduce you to a few new capabilities in spatial statistics. Thank you.
Thanks, Charmista. I want to share 2 new capabilities from the Spatial Statistics team. The first one helps you find analytical confidence when aggregating points, and the second one helps you build trust when you're working with predictive models. This map shows 2 million GPS points for marine vessels off the coast of Peru, and we can't really answer meaningful questions just working with the raw points, so we should aggregate them to a grid. But that will bring up an important question. What bin size should we use? And honestly, it's something that many of us will select based on a gut feeling, isn't it? We find something that looks good enough, move on, and hope that it all works out. But this decision really matters. The patterns are decided by the bin sizes, and the stories that we tell and the maps and the analysis that come after are decided by the bin sizes. And this relates back to the modifiable aerial unit problem, one of the most challenging problems in geography, and one that we really like to warn you about, but seldomly make tools to actually help you address. So the largest bin sizes summarize data, but often struggle to preserve the spatial patterns. And the smallest bin sizes preserve the spatial patterns, but often struggle to summarize the data. So how do we strike the right balance? Well, there's a new tool called Evaluate Bin Sizes for Point Aggregation, and here's how it works. The tool will test multiple bin sizes for your point data from smallest to largest, scoring each bin size based on 2 opposing goals. The first one is to summarize as much as possible, but the second one is to preserve the spatial patterns in the data. And these goals go in opposite directions, so it's a pretty tricky balance to get right, but the tool's job is to find the bin sizes with the best compromise. Let's have a look at the results. So there's a lot to look at here, but I'm going to guide you. First, look at the chart at the bottom. It shows all the bin sizes that were tested and their scores. And I want you to look at the peak in this line here and the orange area around it. It highlights the suggested bin sizes. And the bin size with the top score is shown on the map. Now we can look at marine traffic patterns with a more deliberate bin size. And this helps build confidence when you have to decide that, and trust with the analysis that would come after. Speaking of trust, I want to switch to another problem, building trustworthy predictive models. This map shows human anaplasmosis, a tick-borne disease, and the counties in pink report confirmed cases. And you might notice that there's an entire state missing, Minnesota. We actually have data for Minnesota, but let's pretend for a moment that we don't. That would be the perfect test for a predictive model. So we've trained a gradient-boosted model using health and climate indicators plus iNaturalist observations, and the model reported a sensitivity of 50%, meaning that it should correctly predict about 50% of the infected counties in a new area. But when we predict to Minnesota, the model actually fails to detect any of the infected counties. So what went wrong? Well, there's 2 issues that I want to talk about. The first one is that the model was validated randomly, not spatially. And that means that the model was tested in locations that were too similar to what it already knew. And that makes the models look better than they are. That's a big problem because Minnesota is this new spatially contiguous area that we need to predict to. And the second issue is that anaplasmosis is actually quite rare, so the models really struggle to find meaningful patterns from such imbalanced data. What can we do about that? Well, there's another new tool called Evaluate Predictions with Cross-Validation. And here's 2 ways in which it helps. The first one is that it will do spatial cross-validation, which forces your models to prove themselves in spatially contiguous areas that it hasn't seen before. And the second way that it helps is by resampling for rare events so that the models don't get overwhelmed with the majority class. With this setup, The model's reported performance is now about 64% for sensitivity. And this time, when we predict to Minnesota, the model correctly predicts about 60% of the infected counties. And here's why this matters so much. In real-world prediction tasks, we don't have the observations to check against. That's why we were predicting. So we have to rely on the model's reported performance. And this tool gives you a more accurate and spatially aware measure of predictive performance. So whether you're finding some confidence when deciding on a bin size or building trust when you're creating a predictive model, spatial statistics tools contribute to the important work that you all do. Thank you. Back to you, Lauren.
Thanks, Alberto and Sharmishta. Our world needs a lot more than just technology. It needs GIS professionals playing a vital role in what comes next, creating a culture of curiosity, working together, applying science with care. Well, spatial analysis, your work, plays a real role in how decisions get made. So trust really matters. And when analysis is done well, rigorous, transparent, and grounded in the science of geography, it earns that trust and can make a real impact in our organizations and beyond.